So this lecture is about data types in first-order logic. So previously, we used this notation for all xa and existential xa, where the type of these term variables are not specified. So in order to state that, for example, there exists a natural number that satisfies a particular property A, we would write for all x if x satisfies this predicate net, then it satisfies A. So in order to state that this term variable x belongs to particular data type, we would introduce a corresponding predicate, something like this. And for existential quantifier, we would write there exists a term x such that it is natural number and also it satisfies A. So there's nothing wrong with this approach, but it's quite cumbersome to have to introduce a predicate for every data type that we will be using. So in this lecture, we'd like to introduce these data types, which directly specify the type of term variables or terms. So instead of this old notation, now we are going to use this new notation. For all x belongs net, it satisfies A. Now, unlike the previous notation where the data type for this term variable x is not specified, now we explicitly specify the data type for this term variable x. So this proposition reads, for every term x of data type net, or every natural number x, it satisfies A. And similarly, we could write existential x belongs to net such that it satisfies A. So this proposition now reads, there exists term x of data type net, or just a natural number x that satisfies A. So if we compare the previous notation against this new notation, we don't have to introduce new predicate to state that a term variable x belongs to a particular data type. Instead, we introduce this new data type, that's all. So the topic for the lecture today is first order logic with data types. So we will be using this new form of quantifiers such as net A or existential x net A, where these guys are data types. Or in this example, that is the data type for natural numbers. And when we discuss these data types, the main judgment is this one. Term T belongs to data type tau. So this reads term T has data type tau. This is a new form of a judgment, and we will use natural deduction again to define the inference rules for these judgments. So because we are going to use natural deduction for every judgment of this form, for example, term T belongs to data type net, or term T belongs to data type bool, we will be formulating introduction rules and also elimination rules, because we'd like to use this natural deduction. And before we proceed, we'd like to introduce new notation. So previously, here, we just use this symbol A to indicate that term X satisfies this property A. But now we'd like to state explicitly that term variable X may appear inside this proposition. So now, instead of this old notation, we'd like to use this notation for all X in net A of X. So semantically, there's no difference between this one and this one. But this new notation indicates that this term variable X appears inside this proposition A. So it's much clearer than before. And similarly, we may write existential X belongs to data type net such that it satisfies this property A. So again, there's no difference between these two, except that here we explicitly state that this term variable appears inside this proposition. That's all. Now, the notation for substitution is also slightly simpler. Previously, in order to state substitution, we had to use this notation. For example, in proposition A, replace term variable X with the term T. So this was the notation. Now, we use this term variable X along with this proposition A. We can just write A of T to indicate that term T has been substituted for the previous placeholder. So for example, if we have A of X, then we can just simply write A of T to mean that term T is now used for this term variable X. So previously, we had something like term T for X in A, but now we can just use this term T directly between these parentheses. So to summarize, in this lecture, we will be talking about data types so that we can directly specify the type of this term variable in these quantifiers. And the main judgment is this judgment, which says term T belongs to data type tau, and we will be using natural deduction style again. So for every judgment of this form, there will be introduction rules and corresponding elimination rules. And as a slight change to the syntax, we will now adopt this notation. So before we proceed to concrete data types, such as net or bool, let's consider the general data types. General data types that do not depend on particular examples. So the general data types are function types, and product types, and sum types, and unit, and void. So this is function type, and this is product type, and this is the sum type, and this is unit and void. And the terms for these data types, are obtained in a completely similar way, to the simply typed lambda calculus, where we had, for example, implication, conjunction, disjunction, top and bottom. Uh-oh. So the syntax for these terms will be similar to the syntax for the simply typed lambda calculus, because essentially there's no difference. So for function types, we will be using the familiar lambda abstraction, lambda x, but this time we will use this in symbol because we are dealing with the data types. So tau and term t. And we have this lambda application. And we'd like to continue to use the previous syntax for this lambda abstraction and lambda application. And for product type, we have this pair, and we have this projection, first and second. And for this sum type, we have injection left, and we have injection right, and we also and we have this case construct, case p of in left x of t or in right y of t. And finally, we have this unit term and abort term. And the way that we derive all these terms is completely analogous to the way that we derive similar constructs in the simply typed lambda calculus or in the previous discussion. So typing rules are completely analogous as well, and we can even derive beta reductions and eta expansions in the same way. So now it remains to fill this part of the definition with concrete data types such as bool or nat. So remember that these are terms, not proof terms. So they have data types instead of types. So that's a difference, which is indicated in the use of this symbol in the lambda abstraction. But the mechanism of deriving terms is the same as in the way that the same as simply typed lambda calculus, where we derive proof terms in the same way. Now, let's consider concrete data types such as bool and nat. So for example, it's a time to formulate the inference rules for this judgment and also this judgment. And remember that we are going to apply this principle of a natural deduction to formulate the inference rules. And usually, we start with the introduction rules, which states how to derive this judgment. So introduction rules basically convey the idea behind this particular data types. For example, the introduction rules for bool tell us the main idea behind this data type bool. So we design these introduction rules ourselves. And then we try to derive automatically these elimination rules. Elimination rules state how to exploit an existing judgment of this form. So introduction rules takes this form. Some t has a type bool. When you read this rule top down, you end up introducing this bool. So it tells us when we can actually deduce this judgment. And elimination rules tell us how to exploit an existing judgment of this form. This is introduction rule. This is elimination rule. So remember that we will try to design these introduction rules ourselves because these introduction rules are basically the essence of the idea, the essence of this new data type. On the other hand, we will try to derive these elimination rules automatically. So let's start with a simple case, this Boolean data type. So we will formulate the inference rules for deducing this judgment. And the idea behind this bool is it allows us to choose one of two options, and we choose to call these two options true and false. So this Boolean data type allowed us to choose one of two options, namely true and false. So that's the idea behind this Boolean data type. So let's translate our intuition about this Boolean data type into introduction rules. Well, we can choose the first option. So true is Boolean data type. And this is Boolean introduction rule true. And there's another introduction rule. False also belongs to data type Boolean. And this is Boolean introduction false. So these are two introduction rules. These are two inference rules constitute the introduction rules for bool. It tells us the idea behind this Boolean data type. Now let's talk about the elimination rule. Elimination rule starts with a judgment of this form. There exists a term t which is known to have data type bool, and we'd like to exploit this judgment to deduce something else. So in general, it's unknown whether this term t is actually equivalent to true or false. So for example, this term t could be simply a variable. So therefore, we have to provide for two cases. The first case where term t actually is equal to true, and the second case where term t is equal to false. So we will have two branches. So in the first branch, we assume that term t is true, and we continue to evaluate this term t1. And let's say it has a data type tau. In the second case, where term t is false, we evaluate this term t2. And we require that the term t2 should have the same data type tau. Then, whether term t is true or false, we can always find a term of data type tau. Just like the case construct in the simply typed lambda calculus. Now we have found a term of data type tau here, and we decided to borrow the syntax from the sum type. So we use this case construct, case t of true. If term t is true, then we take a t1, and if it is false, then we take a term t2. And we can simplify this term into a more familiar form, which is if then else. So if instead of this case keyword, we could just write if term t, then we take a t1, or else we take a t2. So you can think of this if then else construct as a slight simplification of this case construct. So it is going to have a type tau, and this is Boolean elimination rule. So to summarize, for data type Boolean, terms for data type Boolean include true, false, and if then else. Now we have these introduction rules and an elimination rule. So we can now talk about local reduction and local expansion. Local reduction gives rise to this beta reduction, and it's pretty easy to derive this beta reduction. So remember that beta reduction is all about eliminating detour. Detour constituting where detour is comprised of an introduction rule immediately followed by an elimination rule. So introduction rule immediately followed by elimination rule. So how do we reduce this one? Well, we just take a T1. And there's a symmetric case where the term here is false. In that case, we take a T2. And what about the local expansion? Local expansion starts with a term T of data type bool. How can we expand it? Well, if term T is true, then we take a true. And if it is false, we take a false. So when you write in computer programming, every time you see this pattern, you can always go back to term T directly because this is redundant. So this is the so this concludes the discussion of data type bool. Now let's move on to data type net. So the goal now is we'd like to formulate the inference rules for this new judgment where we introduce this data type net. So data type tau now includes net. And the idea behind this natural number or the definition of a natural number is it's either zero, the definition of a natural number is it's either zero or successor of another natural number. So let's translate this definition into two introduction rules. First, zero is a natural number. So this could be written as natural introduction zero. And the other case is actually an inductive case in the sense that it involves something smaller. And from the property of something smaller, then we derive the same property of something larger. So it's inductive definition. So the definition goes like, if a term T belongs to net, its successor is also net or natural number. So this is natural number introduction rule successor case. So we have just translated the definition of natural numbers into two introduction rules. And as I said before, we can actually derive the corresponding elimination rule automatically. Let's derive the elimination rule. The elimination rule starts with a judgment of this form. Term T has data type net. And what do we do about it? How do we exploit this existing judgment? And again, in general, we cannot tell in advance whether term T is zero or successor of something else. So we have to consider two branches. Or because there are two introduction rules, we have to consider two cases. The first case corresponding to the first introduction rule, and the second case corresponding to the second introduction rule. So for the first introduction rule, we in this case, term T is actually zero. In this case, we take this term T0, and let's say it has data type tau. And in the second case, term T is successor of something. But we don't know what this something is. So let's say it is variable x. In this case, we take this term t of s, and it must have the same data type tau, the same data type as in the first term t0. And inside the term ts, we may use the fact that x is the predecessor of a term t. And according to this introduction rule, the predecessor has the same data type, namely nat. So inside this term ts, we may use this assumption or this hypothesis as indicated by this horizontal bar, the hypothesis that x also belongs to data type nat. So this is the second case. And finally, we can devise a new form of a term to collect all these things in the premise. And it's going to have a data type tau. And we'd like to use the same syntax, a case construct. If term t is 0, then we take t0. Or if it is a successor of x, as indicated here, then we take this term ts. So this is natural elimination rule. So to summarize, for data type nat, so data type nat, we introduce these new forms of terms, 0, successor of t, and case construct, case t of 0, then t, or successor of x, then another term t. And we can repeat the same exercise. We have these introduction rules and elimination rule. So we can talk about eliminating detours or beta reductions. And remember that beta reductions are all about getting rid of detours, intro followed by elim. So it's straightforward to derive these local reductions or beta reductions. So let me just write it. Beta reduction, intro, okay, there are two ways to introduce nat, 0 or successor of t. There are two ways to introduce 0 or successor of t. And let's eliminate immediately. So in this case, we eliminate case 0 of t1 or successor of x of t2. In this case, perhaps we will take this branch, so we just take a t1. So this is the first beta reduction. And the second one is introduce and then eliminate immediately. So now we have this case construct again, 0 of t1 or successor x of t2. This time, we are basically performing pattern matching here. So this successor of t doesn't match with this one, so we take this branch. So we will be reducing the whole term into term t2, but inside the term t2, we may use this variable, new variable x, as indicated by the presence of this hypothesis. So inside the term t, you may use this term variable x. So inside the term t2, you may substitute x with, actually it's a successor, actually predecessor. So if you apply pattern matching this one against this one, then x is going to assume this term t. So you simply replace x with t. So that's the beta reduction, the second one. And eta expansion is also straightforward. Eta expansion, if you have some term t of data type nat, how can you expand it? Well, you perform case analysis if term t is 0, then you just return 0. Or if it is successor of x, then you return successor of x. So essentially, you destruct the term t and then rebuild it. So it still has the same data type nat, this one. So this is the eta expansion. Now we can write the simple functions operating over natural numbers. So the first example is predecessor function. Predecessor. So it belongs to data type nat arrow nat. So note that here we use this symbol because this predecessor function is going to be really function of this data type. It's not of type of this form. For example, A implies B, because this is not a proof term. It's literally a function, something like this one. So it's not this one. It literally takes a natural number, this black box, and returns another natural number. So it has this data type net arrow net. Let's define this predecessor function. Okay, it starts with give me a natural number x, and then I'm going to perform case analysis. If it is 0, then we return 0, where we assume that the predecessor of 0 is also 0 because there's no other natural number before 0. And if this is a successor of y, then we return y. And it turns out that this lambda abstraction has data type net arrow net, because we can show that this case construct has data type net. So that's the first function operating over natural numbers. The second example is the doubling function. So this function tries to double the argument. For example, double 0 is supposed to return 0, and double successor of 0 is supposed to return successor of 0. You can interpret it as 1, and you can interpret this term as natural number 2. And it turns out that you cannot actually define this function double using this case construct, because in order to define this doubling function, you have to have some form of recursion. But the previous elimination rule, this case construct, does not allow us to use recursion. So intuitively, there's no element of recursion here, or in this elimination rule, there's no element of recursion. So it turns out that we can never implement this doubling function using the terms defined so far. There's some element missing, which is recursion. So the last topic in the lecture today is primitive recursion. The primitive recursion is not actually general form of recursion. It is a special case of recursion where a recursive call is made with a strictly smaller argument. So in other words, if you call this recursive function f with some argument, something like this, inside this function call, you may make another recursive call, but the argument is strictly smaller than the original argument. And it is guaranteed that the recursive call eventually terminates, because every time you make recursive call, the argument decreases in size. You have something large here, but you have something smaller here. So primitive recursion has the property that recursive calls eventually terminate, unlike a general recursion. So the goal now is we would like to revise this elimination rule for natural number so that it allows the new form of elimination rule would allow us to use primitive recursion. Currently, there's no recursion here, but we'd like to extend this one with the primitive recursion. So that's the goal. So let me summarize the inference rule so far. For data type net, we have these two introduction rule. This is net introduction 0, and successor of T has data type net if T has data type net. This is natural number introduction successor case. The remaining question is, what is the elimination rule with primitive recursion? So let's do this. So the primitive recursion, the elimination rule with the primitive recursion, it's elimination rule. So it starts with a judgment of this form. We know that term T has data type net, and how do we exploit it? The first case is, what if term T is just 0? In that case, we take this term T0. Let's say it is data type tau. Now, what about term T is successor of something, and we don't know the actual predecessor of term T. So let's just say the successor is X. And in order to introduce the element of recursion, assume that we are in the middle of calling a recursive function f. So here we write, instead of case construct keyword case, we use this keyword rect to indicate that we are in the middle of making recursive call. And let's just say we are currently calling this function recursive function f with the argument of term t. So this is the new context. In the previous elimination form, we just had this one, case t of blah blah blah. But now, in order to introduce the new element, namely primitive recursion, we introduce this recursive function f. So imagine that we are in the middle of calling this recursive function f with the argument t. And what if the term t is 0? Then we just take this t0 as the return value. So this is the first case. And what about the second case? In the second case, term t is a successor of x. In this case, again, we take term ts, and it should have data type tau, the same data type. Now, inside this term ts, of course, we may use this predecessor, which is stored in term variable x. So we may use this assumption or this hypothesis as indicated by this horizontal bar, the assumption that x has data type net, which is justified. This is justified by the introduction rule. So the predecessor must have the same data type net. So we have the first hypothesis, which says that the predecessor is of the same data type. So far, everything is the same as the previous elimination rule. And what's new here is we allow another recursive call inside this term ts. And this recursive call will follow will obey the syntactic constraint, which is you may make another recursive call f, but the argument must be x. That's the syntactic constraint imposed by the primitive recursion. So to summarize the story so far, we are in the middle of processing this recursive function call f of t. And if the argument is 0, we just return this t0. If term t is successor of x, we choose this branch. We evaluate this term t of s. Inside this term ts, of course, you may use the fact that x is a natural number. And in addition, you may use another recursive call, but the requirement is you must use the argument x, which is strictly smaller than the original argument. The original argument t is a successor of x. Now, if you want to make another recursive call, the recursive call must be made with a strictly smaller argument, namely x. So inside this term ts, you may use the assumption that f applied with argument x has the same data type tau. So you can think of this one as the result of recursive call inside this function body. Now, this is going to be natural number elimination rule, and the syntax for the term here, it is going to have data type tau, this one and this one, and the syntax is if this recursive call f of t is f of 0, then we take term t0, and if it is f of successor of x, then we take a term ts. So it's similar to pattern matching. So we are comparing this f of t against f of 0 and f of s successor of x. And remember that inside this term ts, you may make another recursive call, but the recursive call must be made with this argument x, which is strictly smaller. Now we can tell that the function call, this recursive function call, eventually terminates because every time you make a recursive call, the argument strictly decreases in size. So in this case, the argument was successor of x, but another recursive call is made with x. So that's the new form of elimination rule, which now involves this primitive recursion. And another thing to note is this f of x is not function application. So it may be confusing at first, but the best way to interpret this f of x is you may assume that it is just a variable. If it is still confusing, you may use instead of f of x, just use another variable like fx or something like this. It's a syntactic convenience for visual clarity. So it may not be obvious from this variable, it is actually function call. It corresponds to the function call. But if you choose this form of variable, it's syntactically or visually clear that it denotes recursive call. So to summarize, this f of x is not a function call, or lambda application is not function call. It's just a variable. So now we have the definition of terms for natural numbers. It's either 0 or successor of t or recursive recursive f of t of, if this is f of 0, then take this term. And if this is f of a successor of x, then you take another term. And note that these are variables, this f and this f. So for example, you may use another name d, function name d for this f, and you may use another term variable y instead of x here. So this is the definition of terms for data type net. And now we have these introduction rules, and we have this elimination rule. So again, we can repeat the same exercise, namely beta reductions and eta expansion. So let's talk about the beta expansion first. Beta reduction is about eliminating detour, intro followed by elim. So the first case is easy. So let's talk about the second case, this one. So the question is, we have intro form followed by elimination form of f0 term t1, let's say, and of f of a successor of x term t2. So it is basically intro followed by elim. So this inner rectangle indicates intro rule, and this outer rectangle indicates elimination rule. And the question is, how do we reduce the whole term? So needless to say, we will take the second branch, because if you compare this one against this one, it doesn't match. So we will not take this branch. So we will take this branch. So this one reduces. We will take this branch, term t2. And inside the term t2, we have two variables. The first variable x and the second variable f of x. Remember that this f of x that appears here is not function call or lambda application. Semantically, it denotes the result of a function call, recursive function call, but syntactically, it is variable. So inside this term t2, we have two variables, term variable x and term variable f of x. And now you have to provide some way of replacing these two variables. And it's easy to replace x because x is going to be basically term t. And what about f of x? And semantically, this f of x is the result of recursive call of the same function f with argument x, which is t. So basically, f of x must evaluate something like f of t. So whatever comes here should denote f of t. And it's pretty easy to create a term that denotes f of t. We simply make the whole copy of the whole term, make a small change, which is replace the argument. So let me just make the whole copy of the whole term here, recursive f, blah, 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 of f0 term t1, f of a successor of x is going to be term t2. But the argument is now t. So that's the beta reduction. And eta expansion is also similar to the previous case. But how do we expand it? Well, we introduce a dummy recursive function. If this is f of 0, we return 0. And if this is successor of x, then we return successor of x. So in this particular case, this recursive construct does not actually make a recursive call. So this concludes the discussion of data type net. Let me just show you an example of using this recursive construct. So previously we failed to define this function double. Now we can now we can implement this function double. So the specification goes like, if the argument is 0, then it returns 0. If the argument is successor of something, then we first make recursive call with a strictly smaller argument. Original argument is a successor of x, but now the argument to the new recursive call is x, strictly smaller. So it is guaranteed that the recursive call eventually terminates. Now you add 2. So basically what this thing says, twice x plus 1 is 2x plus 2. And it's pretty easy to define this one. Double, it has a data type net arrow net. So the definition is, give me a natural number x, then let me make a recursive call with the function d. And if argument is 0, then you return 0. Okay, you return 0. Or if this is successor of something, then you make a recursive call first with a smaller argument y, and then apply successor function twice. So that's all. So this is the recursive function using this new form of elimination. And in code programming, the elimination rules are automatically derived. And these elimination rules are equipped with primitive recursion. So for you, it suffices to translate the introduction rules into code definitions. So in code programming, you never write the elimination rules yourself, because once you provide the introduction rules, code automatically derives the most accurate elimination rule for you.